Hello viewers, in today's session we are going to discuss another important problem from continuity and discontinuity of functions. So here in this class we are going to discuss this problem in which we have to find all the points of discontinuity of this function, that is f of x is equal to greatest integer of 4 over pi, and here we have cos inverse of x plus 2, and this the bracket indicates the greatest integer function, right? So we'll find out all the points of discontinuity of this function f of x using simple concepts, right? So let us start. So now see here, the greatest integer function is involved, right? And let us first take this function as p. So let us take p is equal to 4 over pi, and we have cos inverse of x plus 2. So now this function f of x, it takes the form greatest integer of p, where p is 4 over pi cos inverse x plus 2, right? Now see, we know that the greatest integer function is discontinuous at all integers, right? Now if we have the function f of x is equal to greatest integer of x, then this function is discontinuous at all values of x belonging to the set of integers. So it implies that this function, that is the greatest integer function, is discontinuous at 0, plus minus 1, plus minus 2, plus minus 3, and so on, right? So we'll use this concept to find out the all the points of discontinuity of this function. So assuming this function as p, we have greatest integer of p. Now this function f of x is discontinuous. F of x is discontinuous at all values of p for which p belongs to the set of integers, right? So whenever p is an integer, then this function f of x is discontinuous, right? So now let us first consider this inverse function, that is cos inverse x plus 2, right? From inverse trigonometric functions, we know that the range of cos inverse theta is given by this interval, that is 0 to pi. So cos inverse theta belongs to this interval, that is 0 to pi, or in other words we can also write cos inverse theta is greater than or equal to 0, but it is less than or equal to pi. So 0 to pi is the principal value branch of cos inverse function. Now let us substitute theta is equal to x plus 2. So we have now 0, and here we have cos inverse of x plus 2, and here we have pi. So what we have done, we have replaced this theta by x plus 2. So cos inverse x plus 2, it lies between 0 and pi, and remember these two endpoints are also included. So now to get this function p, let us multiply this entire inequality by 4 over pi. So here we have 0 times 4 over pi. Here we have 4 over pi cos inverse x plus 2, and here we have pi times 4 over pi. Now this term is 0. So we have this term, that is 4 over pi cos inverse x plus 2, can be written as simply p, and here pi and pi get cancelled, so we are left with 4. So now we have this inequality, that is p greater than or equal to 0, but less than or equal to 4, or in other words we can write p belonging to this interval, that is 0 to 4, where p denotes 4 over pi cos inverse x plus 2. So now to find the points of discontinuity, this p has to be an integer, because we have just claimed that this function f of x is discontinuous at all points where this p, that is this function, belongs to the set of integers. So p belonging to this interval, and here we have 0, then we have 1, 2, 3, 4, right? So whenever p is an integer, for example, p is 0, p is 1, p is 2, p is 3, and p is 4. So for p is equal to 0, p is equal to 1, p is equal to 2, p is equal to 3, and p is equal to 4, this function f of x is discontinuous, right? So for these values of p, let us find out the values of x, because here we have to find all the values of x for which this function is discontinuous. So now when p is equal to 0, then here we can write p is equal to 0. So we have 0 is equal to 4 over pi cos inverse x plus 2. Now we can multiply here 0 by pi and divide the result by 4. So we have simply cos inverse of x plus 2 is equal to 0, right? And we can write x plus 2 is equal to cos of 0, and cos of 0 is equal to 1, right? So we have a linear equation. So x plus 2 is equal to 1, so x is 1 minus 2, that is minus 1. So we have one point, that is x is equal to minus 1, where this function is discontinuous. Now similarly we can find for p is equal to 1. Here we write 1, here we have 4 over pi, then we have cos inverse x plus 2. Now we can easily solve this equation, multiplying 1 by pi, dividing by 4. We have cos inverse x plus 2 is equal to pi by 4. So now we can write x plus 2 is equal to cos of pi by 4, that is 1 over square root of 2. Now taking x is equal to 1 over square root of 2 minus 2. So we can shift this 2 to the right hand side. So the second point is 1 over square root of 2 minus 2. Now let us take p is equal to 2. So when p is equal to 2, we have 2 is equal to 4 over pi cos inverse x plus 2. So we can solve this equation. We have cos inverse of x plus 2 is equal to 2 pi by 4, right? 2 pi by 4, this is pi over 2. So we have x plus 2 is equal to cos of pi by 2, because we have cos inverse x plus 2 is equal to pi by 2. So x plus 2 is equal to cos pi by 2, and cos 90 is equal to 0. So we have x plus 2 is equal to 0. So x is equal to 0 minus 2, that is minus 2. So the third point is x is equal to minus 2. So now let us take p is equal to 3. So when we have p is equal to 3, then we can now write 3 is equal to 4 over pi cos inverse x plus 2. Now we can write cos inverse x plus 2 is equal to 3 pi by 4. So here we multiply 3 by pi and divide by 4. So now we have x plus 2 is equal to cos of 3 pi by 4. Now we can find out the value of cos 3 pi by 4 by cos pi minus pi by 4. Right? We can directly use the value here. See, cos pi minus pi by 4 is minus cos pi by 4, because cos pi minus theta is minus cos theta. So here we have minus 1 over square root of 2, because cos pi by 4 is 1 over square root of 2. So now we have this equation x plus 2 is equal to minus 1 over square root of 2. So from here we have x is equal to minus 1 over square root of 2 minus 2. So the fourth point is minus 1 over root 2 minus 2. So now finally we can take p is equal to 4. So we have 4 is equal to 4 over pi, and here we have cos inverse x plus 2. Now we can write cos inverse x plus 2 is equal to 4 pi multiplying 4 by pi and dividing by 4. Here 4 and 4 get cancelled, we are left with pi. So x plus 2 is equal to cos of pi, right? Okay, so cos pi is equal to minus 1, cos 180 degrees is equal to minus 1. So x is minus 1 minus 2, taking 2 to the right hand side, we have minus 3, right? So the fifth point is x is equal to minus 3. So viewers, from this discussion we have seen that this function f of x, which is greatest integer of 4 over pi cos inverse x plus 2, this function is discontinuous at 5 points, right? And the points are given by x is equal to minus 1, then we have x is equal to 1 over square root of 2 minus 2, then x is equal to minus 2, and x is equal to minus 1 over square root of 2 minus 2, and x is equal to minus 3. So we have 5 points of discontinuity of this function involving the greatest integer function. So whenever this function, that is 4 over pi cos inverse x plus 2, it takes these values, that is 0, 1, 2, 3 and 4, then this function is discontinuous, right? Because in that case x is given by these values, and these values corresponds to the discontinuity of the function. Hello viewers, in today's session we are going to discuss another important and conceptual problem from limits. And here we have to evaluate this limit, that is limit x tends to 0, and here we have tan of pi by 4 plus x, and the whole power is pi square over x, right? So to evaluate this type of limit where we have a function which is raised to some another function, then we'll use a particular rule, right? So let us first quickly see the rule, how to evaluate these kind of limits. So now consider two functions f1 and f2. So if we have limit x tends to a, here we have f1x raised to some other function, say f2x, right? And if limit x tends to a, f1x it tends to 1 or it is equal to 1, and the limit x tends to a, f2x, and it tends to not defined or infinity, then this limit can be evaluated by using this result, that is e raised to limit, and here we have x tends to a, f2x, and f2x is multiplied with f1x minus 1, right? So whenever we have a limit of this form, and we have these two conditions, limit x tends to a, f1x tends to 1 when x tends to a, and limit x tends to a, f2x it tends to not defined or infinity, then this limit is equal to e raised to, where e is the exponential number, limit x tends to a, f2x, and here we have f1x minus 1. So let us first satisfy, or let us first test these two conditions for the functions f1x is given by tangent of pi by 4 plus x, and here f2x is given by pi square over x. So limit x tends to 0. Now if we compare this limit with this one, then the value of a is given by 0, right? So a is 0, so limit x tends to 0. f1x is given by limit x tends to 0, and we have f1x as the tangent of pi by 4 plus x. Now this limit can easily be evaluated by simply taking x is equal to 0 over here. So we have 10 pi by 4 plus 0. So this is the tangent of pi by 4, and 10 pi by 4 is 1. So this condition is satisfied, that is limit x tends to a, f1x tends to 1 when x tends to 0, right? Now let us see this limit. So we have limit x tends to 0, f2x, and here we can write limit x tends to 0, and f2x is given by pi square over x. Now we can easily see that this is pi square limit x tends to 0, 1 over x. Now this limit tends to infinity when x tends to 0. So we have this limit tending to infinity. So we have seen that these two conditions are satisfied by these two functions. And now this limit, let us call this limit as L, right? So the value of the limit L is now given by this rule, that is e raised to limit, and we have x tends to 0, and f2x is given by pi square over x, and f1x is given by a tan of pi by 4 plus x, and here we have minus 1. So now we have to evaluate this limit. So now we can write the limit L as e raised to limit x tends to 0. We have pi square over x, and here we have tan of pi by 4 plus x. Now we can apply this result from trigonometry, that is tan of a plus b is given by tan a plus tan b divided by 1 minus tan of A and tan of B, right? So our A is pi by 4 and B is x, right? So now we have here a tan pi by 4 plus tan of x divided by 1 minus tangent of pi by 4, and here we have tan of x. Now tan pi by 4 is 1, so we have 1 plus tan x, and here we have 1 minus tan x, because tan pi by 4 is 1, 1 times tan x is tan x. So we can now replace this term, that is tan pi by 4 plus x, by this expression. So now we have 1 plus tan of x divided by 1 minus tan of x, and here we have minus 1, and now we have to simplify this expression. So now we can write L is equal to e raised to pi square. We can take pi square in front of this limit notation, and we have limit x tends to 0, 1 over x, and here we have 1 plus tan x, and multiplying this 1 by 1 minus tan x, we have minus 1 plus tan of x, and here we have 1 minus tan of x, right? So now this one and this one get cancelled, so we have e raised to pi square limit x tends to 0 and 1 over x, and here tan x plus tan x is 2 tan x divided by 1 minus tan of x, right? So we can now write e raised to pi square and we can take this 2 over here, and we have limit x tends to 0 tan x, and we can take this x in the denominator of tan x, and here we have limit x tends to 0 and 1 minus tan of x, right? And this entire term is in the uh, power of e, right? So now this limit, that is limit x tends to 0 tan x over x is equal to 1 from the standard results from limits. So this limit is equal to 1. So here we have 1, and limit x tends to 0, tan x is equal to 0, because tan x can be written as sin x over cos x, and when we find limit x tends to 0, then here we have sine 0, and here we have cosine of 0. So sine 0 is 0, and cos 0 is 1, so this is 0. So this limit is 0 and this limit is 1. So now we can write e raised to 2 pi square multiplied by 1. This limit is 1, and we have 1 minus 0. So this is e raised to 2 pi square times 1 over 1. 1 minus 0 is 1. So this is e raised to 2 pi square, right? So viewers, the value of this limit is equal to e raised to 2 pi square. So we can see that by using this result, that is limit x tends to a f1x raised to f2x, is given by this expression, provided we have these two conditions, we can easily find out the values of these kind of limits.